Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. Okay, so this is a new sorting algorithm that we have to discuss. One of the most, I would say, interesting sorting algorithms, and to be very honest, one of the most important as well. Right, we're talking about quicksort. Right, now quicksort is a bit different than the other sorting algorithms, because in order to maintain the efficiency of quicksort, we actually implement the concept of randomization. Right, quicksort involves the concept of randomization in order to make sure that it achieves the best possible efficiency. If you don't implement randomization, then quicksort can lead to extremely bad worst case complexities. That's why introducing randomization helps us a lot. Right, now you might be thinking, what is randomization and what exactly is meant by randomization? So let's talk about it. Okay, so what are randomized algorithms? In randomized algorithms, what do we do is we have an algorithm that takes some input and we expect some corresponding output out of the algorithm, right? And there is an element of randomization. We try to add some more input that adds some element of randomization, right? That somehow, let's say, randomizes the input, or maybe during the process, if we are taking some value, it takes it as a random value and then prepares an output, right? These kind of algorithms that involves an element of randomization are called as randomized algorithms. And the best complexity of quicksort is actually also received or achieved using randomized quicksort, or the quicksort with randomization. Now, how exactly quicksort works? Now, quicksort algorithm is very simple, to be very honest. If you try to understand the basic nuances around quicksort, then So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different. And a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video.
Overall algorithm is very simple. What you have is an array, right? In your array, let's say you define a range L to R, right? In this array, what do you do? You pick an element X. You pick an element X. This element you call as the pivot element. Now you can pick this element X deterministically or randomly. For example, you can define a methodology that always this element is going to be my X. Or maybe you can add some element of randomization. So what we can say is that let's try to pick this element X with randomization, because we are talking about randomized quicksort. Right. I'll also talk about what will happen if there is no element of randomization. Okay. Now, what we will do is we will pick X from the given array randomly. So how do you pick randomly? From L to R, you are going to pick a random index, right? And on that random index, whatever element is present, that element is going to be a pivot element, right? So on that particular random address, let's say this L to R is going to give you an index randomly between L to R, right? Now, whatever is the random index, you check what element is present at that random index, and that element is going to be your pivot element, right? Now, what you have to do here is, once you have identified your pivot element, you are calling it as pivot because you do some operation on this. You can name it as anything, right? What you do is you try to divide your array into two parts, right? Once you have identified the pivot, you try to divide your array into two parts such that the left part has all the elements less than X and the right part has all the elements greater than or equal to X, right? So you segregate elements. Let me write it here. We segregate elements in the array into two parts such that left part has all the elements less than X and right has all elements greater or equal to X, right? This is the segregation that we are going to do. That once we have randomly picked the pivot element, what we are going to do, we are going to segregate the elements such that everything on the left part is having the values less than X and everything on the right side is having a value greater than or equal to X, right? And then what we are going to do, we are going to recursively repeat the process just for the left half and recursively repeat the process just for the right half. So for example, let's say you have a set of elements like 5, 9, 3, 1, 2, minus 1. Okay. So let's say you randomly pick the element 2. 2 is your pivot X, right? So what you are going to do, you are going to segregate the elements such that everything on the left side is less than 2. Everything on the right side is greater than or equal to 2. And one thing that you need to understand is the left and the right side don't need to be sorted. The elements here can be arranged in any random order, right? They don't need to be sorted, right? The only segregation is that everything on the left side is less than X. Everything on the right side is greater than or equal to X. Their, I would say, arrangement among themselves can be random, right? So for example, let's say in the same array, if we try to do the conversion, then maybe we can get something like this. So let's say we get something like 1 minus 1, then 2, 5, 9, 3. Okay. Now you can see this is the left part. Everything on the left side is less than x. Everything on the right side is greater than or equal to x. Right. So now what will you do? On just this left half and just this right half, you are going to repeat the process. Right. So if you repeat the process just on the right half, let's say you pick the random element as 3. Okay. So what you are going to do, you are going to segregate the elements such that everything to the left of 3 is less than 3. Everything to the right of 3 is greater than or equal to 3. So let's say the segregation looks something like this. Okay. You have segregated this 3. And similar thing you will do here. Similar thing you will do here. Let's say the pivot element you pick as -1. So everything greater than -1 is kind of here. Now you can see the left part is now sorted. The right part is somehow somewhat sorted, somehow somewhat not sorted. You are again going to repeat the process. Now just in 2395, you are again going to pick a pivot element. Let's say I picked the pivot this time as on the left side as 3. This is already done. On the right side, let's say I'm going to pick as 9. And again, I'm going to arrange less than 9 on the left side, otherwise greater than or equal to 9 on the right side. And by repeating this process, you can see now we have got a sorted array. So what I'm trying to mention here is that if let's say you have an array and within that array you found a pivot element x, what do? You segregate the elements of the array in the same array. In place we are going to do, right? In place means in the same given array we are going to do this thing, right? And what we are going to say is that we will segregate the elements such that on the left side there is everything less than x. On the right side there is everything greater than or equal to x. We are not going to make new arrays. This is something that you have to keep in mind. We won't be making new arrays and segregate everything in the same array. So we will do the segregation in the same array. We are not going to create new arrays. This segregation will happen in the same array, right? And once this segregation is done for x, now just for the left part and just for the right part, I'm going to repeat the process. I'll again find some pivot y here, then segregate the elements based on less than y and greater than or equal to y. Same thing here, we'll get a y here, less than y, greater than or equal to y, and so on. We will keep on recursively repeating the process on the left part and the right part. And the left part and the right part do not need to be in equal partition, right? Left and right part might not be equal halves. This is something we have to keep in mind, that these might not be equal halves, right? So whatever left and right part we are getting, we'll try to segregate out our logic such that we go and do this segregation on the left part, then on the right part recursively. So recursively, that means we are going to keep on repeating. At last, what will happen is we will be having a single length array. Single length arrays are already correctly segregated in whatever order you want. From there, you are going to repeat. You are going to come back. So it's kind of like similar to merge sort, but in merge sort, you used to create new arrays. On those arrays, you recursively used to sort the left half, sort the right half, and then do the merging. Here, what we are going to do, before we go to the left or the right side, we pick up pivot, segregate the element less than pivot on one side, segregate the element greater than equal to pivot on the right side, and then whatever left side you got, you recursively go and apply the same algorithm there. Whatever right side you got, you recursively go and apply the same algorithm is there. That is quicksort for you. This is the overall, I would say, definition of basic randomized quicksort. Now we have to figure out how can we implement the segregation algorithm. What is a segregation algorithm? So segregation algorithm is the algorithm using which if we have the access to the pivot, that somebody gave us the pivot, we are able to distribute our elements in the array into two parts such that everything on the left side is less than x and everything on the right side is greater than or equal to x. This segregation algorithm is also known as the partition algorithm. This is also called as the partition algorithm, right? This segregation algorithm is also called as the partition algorithm. So for example, let's say we consider the pivot element x is equals to 32 in this given example. Now, how can we segregate the elements such that we have the elements in the array in two parts? We have the elements in the array into two parts such that everything on one part is less than x, everything in the other part is greater than or equal to x, right? Now, you can actually implement this strategy using two pointers. So let's say you have an array and the range of the elements is from L to R. Okay. L to R. Cool. Now what we are going to do, we can maintain two pointers. So let's say this element is M. Right. So we'll maintain one pointer M that is going to start from L. Okay. And we are going to maintain another pointer I that is also going to start from L. And what we are going to do, we are going to move I again and again multiple times. We are going to move I at every element. And what we are going to say is that all the elements present on the indexes less than M are for sure less than X, right? So all of the elements that are going to be to the left of the index M, wherever on whatever index M is pointing to, whatever are the elements that are going to be on the left side of M, we are going to say all of those elements are less than X, right? This is something that we are going to start with. Cool. And then what we are going to do is starting from index I, whatever index I is actually pointing to, we will get this element A. Let's say there is some element A. We are going to check if A is less than X, right? We are going to check if the value of A is less than X. If the value of A is less than X, then what we are going to do? We are going to swap the element at index I with the element at index M. Here you might feel that both of them are at the same index. So sir, what exactly you are talking about? So let's take a generalized term. So let's say I is present somewhere here, M is present somewhere here. Okay. So what I can say is that in this region, all of the elements are less than X because everything to the left of M is actually less than X. We have assumed that, right? All the elements present at the indexes less than M are for sure less than X. So all of these elements are less than X. These elements we are still considering. Okay. Now we are at some element A. And we checked that A is less than X. If A is less than X, then A should be lying to the left of M, right? A should be lying to the left of M. So what we are actually going to do is, if A is less than X, we are going to swap the element present at index I and present at index M. That is, let's say this element is B and this element is A, right? And we know that everything to the left of M is less than X. And this value A is also less than X. I want to throw this A to the left of M. What I'm going to do? I'm going to swap both of them. So I'll swap this B with this A. And then I will do M++. I will move M ahead, right? That means the range where you have the elements less than X increased, right? Now all of these four elements are less than X. And then you move I also. Let's say this element is not less than X. This element C is not less than X. You won't do anything. You just do I++. Let's say this element D is there. This element D is less than X. What you're going to do? You're going to swap. Let's say this is some element T. So you're going to swap the element at index M and the element at index I. Right. And then do M++ and I++. And now if you carefully see, this whole range this whole range is having all of the elements less than x, and so on. This is how slowly and steadily what we are going to do. We are going to segregate out all of the elements such that when the iteration ends, that is I surpasses the whole, I would say, array, then everything to the left of m is going to be less than x. Everything to the right of m is going to be greater than or equal to x. This algorithm is going to be called as the partition algorithm. So if you want to write the partition algorithm, you can say partition. You're going to get an array and you're going to get LR, that is the range in which you have to do the partition, and you will get the value x. X is the pivot. Okay. Cool. Now, if I give you this example, okay, let's say the pivot element here is 32. Okay. And the range is this L to this R, that is 0, 1, 2, 3, 4, 5. Okay. So first of all, I have the access to, let's say, pivot index. Let's say we will be given pivot index. Pivot index is 2. So the pivot element is 32. What I'm going to do is, I'm going to swap this pivot element with the last element. This pivot we are going to get randomly, right? I'm going to swap this random pivot with the last element. You might be feeling, hey, why do you want to swap it with the last element? I'll show you in a moment. So if you swap this with the last element, 32 comes here and 9 comes here. Now what I'm going to do is, the partition algorithm I'm not going to apply to the whole array. I'm going to just apply from L to R minus 1. In this region only, I'm going to apply the partition algorithm such that in the left part everything is less than x, in the right part everything is greater than or equal to x. So let's see. Let's start applying. So let's say we have m here and we have I here. Okay, cool. Everything to the left of m is less than x. There is nothing to the left of m because m is currently at 0. Now you compare. Is 50 less than 32? No. I plus plus. Is 23 less than 32? Yes. That means we are going to swap 23 with 50. We will do I plus plus and we do m plus plus. Is 9 less than 32? Yes. So we swap m plus plus, I plus plus. Is 18 less than 32? Yes. So we are going to swap m plus plus, I plus plus. Is 61 less than 32? Is 61 less than 32? No. 61 is not less than 32. I plus plus. And now you can see you reached R. I just wanted to put the loop till L to R minus 1. We will loop from L to R minus 1. Now you will say, why you are looping from L to R minus 1? Because now inside this array, can I say m is pointed at index 3? That means in the range 0 to 2, we have everything less than x. In the range 3 to n minus 1, we have everything greater than or equal to x. Right? And we are damn sure that our pivot element is present at the last index, because whatever pivot index we chose, we swapped it with the element at the last index. So now technically what I'm going to do is, I'm going to store this pivot at index m, right? So I will swap 32 with 50. I'll swap 32 with 50. Why I'm doing that? Because now this particular element is the element whose left side is having everything less than 32, whose right side is having everything greater than or equal to 32. Right? You might feel, why is this important? Let's see. So let's say that you picked an array. Inside that array, you picked a pivot element. For example, your pivot element came as the largest element. Or let's say, for an even simpler case, let's consider your pivot element comes as the smallest element. Okay, smallest element of the array is your pivot element. So what you are going to do? you are going to segregate the elements such that everything less than the pivot is on the left side, everything greater than the pivot is on the right side. Now you don't even have anything less than the pivot. So your left side is going to be empty and everything will be greater than or equal to x. Can I say that? So your initial space was of size n and it is still of size n. It is still of size n. Now let's say you again randomly picked an element and you again picked the same element pivot. You again picked the same element pivot, which is the smallest element. Again, you won't be able to segregate anything on the left side because there is nothing less than the pivot, because this pivot is the smallest element. This pivot is the smallest element, right? So you won't be able to pick anything for the left side and the whole array is going to be greater than or equal to pivot. So again, left side is not present. And again, this right side is greater than or equal to x. And let's say you again picked the pivot, because at last what we have to do? We have to first segregate, then apply the same algorithm of partition on the left side, same algorithm of partition on the right side. Now, let's say I again applied partition on the right side because left side doesn't exist. And again, I got the same pivot because we are randomly picking the pivot, right? There is a probability that every time you pick the same pivot, and let's say every time you pick the smallest pivot, then you won't be having any space which is less than x, and the whole array will be greater than or equal to x. So can I say this will go infinitely? This will go infinitely, right? Because you are again picking the smallest element and just doing this. But what if I try to do something like this? That is, I push my smallest pivot on the last index, right? This is the pivot element, and then segregate in my array everything less than x and everything greater than or equal to x. Still there won't be anything less than x. This is going to be empty. And now this whole range is going to be greater than or equal to x. M will be pointing at this index. I will be pointing at this index, right? And now what we will do? We will swap x with the element at index m. What we are sure about here is that everything to the left of x is less than x. Everything to the right of x is greater than or equal to x. So this time I don't need to consider this index, and my right space is actually going to be this area. So in one iteration, I will definitely reduce one length. Now let's do the same thing here. Let's say we got the smallest element. This was the smallest element x. We push it on the rightmost index and again do the segregation. When you again do the segregation, you don't get anything for the left side. Everything is greater than or equal to x. So technically your m is pointing here. Your m is pointing here. And now again you will swap this smallest element on this. And now what you can say is that everything on the right side, everything in the right side is greater than or equal to x. You have nothing less than x. So by swapping my pivot index or pivot element at its correct index, because this m is the correct index for the pivot. This is the correct index for pivot. Because now based on this index, everything to the left is less than pivot, everything to the right is greater than or equal to pivot. So when I'm going to segregate my array in the left part and the right part, if let's say this index is m, I'm going to segregate it from L to m minus 1 and m plus 1 to r. What this will help us is, this is never going to lead to a infinite complexity, that the algorithm is going to go infinite again and again. Because here you just saw, right, that if let's say there is nothing on the left side and everything is greater than or equal to x, you can again and again pick the same pivot. And because you are not even reducing even a single element, it will lead to infinite complexity. But here, can I say that if the number of operations to apply quicksort on n length array, the number of operations to apply quicksort on n length array is t of n, then can I say that in every operation what you are doing, you are in the worst case. This is the worst case, right? This is the worst case where you are only reducing a single element, right? Here you are distributing approximately in half of the length, but here this is a single element and this is n minus 1 length. So I will say that if the number of operations to apply quicksort on n length is T of n. This is going to be equal to what? Number of operations to apply quicksort on length 1, because this is now the left side. This is the single length. And technically you don't even need the single length because that's already sorted. So you can say this is equals to T of n minus 1. That is the number of operations you will require to apply quicksort on the n minus 1 length array. This is the n minus 1 length array. Right? This is the n minus 1 length array. And once you have extracted out how many operations you require for n minus 1 length array, can I say you will add order of n for the partition, because you can just see that the partition algorithm is going to work for order of n time, right? You're just using 2 pointers and moving 1 pointer ahead and the second pointer ahead. So the partition algorithm is going to take order of n time for segregating out the elements based on the pivot in the n length array, plus whatever is the time complexity for the recursive call on the n minus 1 length array. If you solve this relation, then T of n minus 1 will be equal to T of n minus 2 plus order of n. T of n minus 2 will be equal to T of n minus 3 plus order of n. And technically, if you don't want to write order of n, you can say C of n, some constant multiplied by n, some constant multiplied by n minus 1, constant multiplied by n minus 2. T of n minus 3 will be equal to what? T of n minus 4, that is the number of operations required to apply quicksort on the n minus 4 length array, plus C of n minus 3, and so on. At last, T of 2 is equals to T of 1 plus C into 1, or you can say C into 2, right? Then T of 1 will be equal to T of 0 plus C. If you add up all of this, why do you want to add up all of this? Because the total number of operations is what? Total number of operations is the value of T of n minus 1 plus C of n. If you put T of n minus 1 here, then that value is dependent on n minus 2. So if you add up all of them, this gets cancelled out here. T of n minus 2 gets cancelled out. This cancelled out. This cancelled out. This cancelled out. At last, you will be left with what? T of n is equals to T of 0 plus Cn minus 1 plus Cn minus 2 plus Cn minus 3, so on and so forth up till C. That is T of n is equals to T of 0 is constant, plus this is sum of n minus 1 natural numbers, that is n into n minus 1 by 2, that we can say is order of n square, right? Let me show you an example. So let's say you have this array. You pick the random element as 2. This is your pivot. It is already at the last index. Okay. So what do you want to do? You want to segregate everything such that everything less than 2 is on the left side. Everything greater than equal to 2 is on the right side. So I will say that the segregation will look something like this. Let's say this is one possible segregation. Okay. This is one possible segregation. So in order of n time, you did the segregation. Now you will apply the same algorithm for the right side. The right side is going to be what? M plus 1 to R, because left side doesn't exist. Now again in this algorithm, in this array, you pick the smallest element of the random during randomization. You swap it here and then you segregate the array such that everything to the left of 3 is less than 3 and right of 3 is greater than equal to 3. So let's say you get a segregation like this. You require n minus 1 operations here because you are not touching this. And now again, m plus 1 to R. Smallest element is already, let's say, on the last index, because why I'm saying always you will pick the smallest element, because randomly you can pick, right? So this is 4. Everything to the left of 4 should be less than 4, otherwise greater than equal to 4. So in n minus 2 operations, you will do this and so on. Can I say the total of all of this is going to be order of n square? That's what I have proven here. And this is the worst case time complexity of quicksort. Worst case time complexity of quicksort, that you always try to divide your array into 2 parts, where one part is of single length, the remaining part is of n minus 1 length. Then again, you divide your array into 2 parts. One part is again of single length, another part is of n minus 2 length. Then again you divide your array into two parts. One part is of single length, remaining array is of n minus 3 length, and so on. And then on an array of length n, for doing the partition you require order of n. So on an array of length n minus 1 you will require order of n minus 1, order of n minus 2, order of n minus 3. That will be total order of n square. This is the worst case time complexity of quicksort, which happens in the case if every time you pick a pivot, which is the smallest element of the given range of elements. Or there can be one more case. If the pivot is every time the largest element, then also the same thing will happen, right? That you will just have the largest element on one side. There is nothing on the right, but everything on the left. So n minus 1 length on the left, then n minus 2 length on the left, and so on. So in a case where, let's say, your length of the array is n, and you randomly pick the pivot recursively every time, which is the smallest element of the range. Every time you do the same pivot, smallest element, smallest element, smallest element, then the time complexity will be order of n square. This is kind of like the worst case analysis. This is the worst case analysis of quicksort. I'm going to write the partition algorithm in a moment, but I believe the worst case analysis of quicksort is clear to everyone. Now, how can we write our partition algorithm? Let's take a look at that. Okay. So let's say in the partition algorithm, I'm going to give the index of x. That is the index of the pivot. First of all, what I'm going to do is I'm going to swap my array's pivot element with the last element. So this is the last element of the array range that we have to do the partition on. I'll first do this swapping. Once I have done this swapping, I will start m with L, I with L, or I can say for I is equals to L, I less than or equal to R minus 1, I plus plus. If we saw that ARR of I is less than, and let's store the pivot also, pivot is equals to ARR of X index is less than the pivot, then we swap the element at I with the element at index M, we do M plus plus. That's it. At last, when this whole for loop is done, I'm going to swap my element, right, at the index M with the element at the index R. That's it. This is going to apply partition algorithm for us. The time complexity of this algorithm is order of n. The space complexity of this algorithm is order of 1. And we are not creating any extra array. We are doing the partition in the same array in the range L to R. Now, a lot of time, a few people consider that when we have to push our pivot at the last index only, why not consider the last index element only? Let's say you have an array like this, and I'm considering that I'm not applying any randomization. I always pick the last element as the pivot. Currently, this is my pivot. So I will apply partition algorithm. Everything on the left side less than pivot. Everything on the right side greater than or equal to pivot. There is nothing on the right side. So in 7 operations, we will be able to segregate all of this. And then I will recursively go on the left side and the right side. Right side is empty. We will recursively go on the left side. Now in the left side, I again pick the last element as my pivot index because now this part is already done. Okay. This part is already done. I'll again pick my last element as my index. As my pivot. So again, I need to do n minus 2 operations, approximately 6, or let me write in terms of n. So we did n minus 1 operations, then n minus 2 operations. In order to segregate everything on the left side as less than 6, everything on the right side as greater than equal to 6. There is nothing on the right side. So what we will do, you'll just go on the left side. Now on the left side, this is going to be your pivot because you decided that every time the last element is going to be your pivot. Right, no randomization. So again, you need n minus 3 operations to segregate everything because your algorithm doesn't know that whether the array is already sorted. So every time it will apply partition in order of n time and then go to the remaining array, which is approximately reducing by a linear length. So this sum of all of this complexity is going to be order of n square, right? So if you don't apply, let's say randomized quicksort, and you apply a normal quicksort where you select the pivot to be always a fixed element, let's say the last element, then for example in the sorted case, the last element can reduce the complexity to order of n square. Or let's say you always pick the middle element, and let's say due to the nature of the data, every time the middle element comes as the smallest or the largest element, then again you will getting order of n square. Now you might feel that with randomization or without randomization, both of the cases we are getting order of n square, then what is the help of randomization going to do? Now in randomization, I said that I pick the element randomly, and let's say there is a probability that every time you pick the smallest possible element or every time you pick the largest possible element. So let's say if there is an array of length 10 raised per 5, how much is the possibility that every time I will pick the smallest element? I am picking randomly and every time I will pick the smallest element. Can I say the probability is extremely less, extremely rare? The probability of picking the smallest element is 1 by 10 is per 5, like that's the only single element. And that too again and again is extremely less, right? Now in 10 is per 5 length is 1 by 10 is per 5 into 1 by 10 is per 4, 1 by 10 is per 3. That every time you pick that single element which is the smallest, this is going to be extremely rare, right? Now due to this rare, I would say, occasion, the complexity of randomized quicksort once in 1 lakh or very large number of combinations comes as order of n square. This time complexity analysis of randomized quicksort is something that we will do that will lead us to understand that the complexity is not going to be order of n square if we consider randomized indexes for the pivot. So now we are going to implement the partition algorithm altogether. So I'll include a vector. Okay. And then what I'm going to say is that int partition. Why int partition? Because we are going to return the index at which our pivot element is present after the segregation. So we'll be having a vector and arr int l int r. Okay. Now what we are going to do, we'll be having access to the pivot index int pi. Pi is pivot index. Let's store the pivot. Int pivot is equals to arr at pi. And then what we have to do is we need to swap the pivot index with the last index, right? We have to swap the pivot index with the corresponding last index. Let's see how can we do that. Okay. So we need to swap pivot index element with the last index. Okay. So I'm going to just write a swap function, right? There is an already inbuilt swap function also that uses iterators. You can use that, right? Or let's try to directly use that also, right? So we can do std swap arr of pi comma arr of r, that is the last index. Okay, we have swapped it. Once we have successfully swapped it, what we are going to do, we are going to start our loop. So we'll say int m is equals to l for int I is equals to l, I less than or equal to r minus 1, I plus plus. We will check if arr at I is less than the pivot. We will swap arr at I with arr at m, and we do m plus plus std swap, std colon colon swap. At last, we are going to swap arr at m with arr at r. That's it. You are going to return it. That is the index at which my pivot is present. Okay. So if you create a vector, so let's have some random data altogether. Okay, so 9, 8, 1, 8, 10, minus 3, 2, 7, 6. Oh, sorry, my bad. Let me write again. 9, 8, 7, 3, minus 1, 2, 5, 10, 11, 4. Okay, and let's say I say that we pick something randomly, right? So what we can do is we can use a random number generator in the corresponding language. So every language has some functions using which you can generate data randomly. Okay, so what you can do is uh, let's see. So now we need a bunch of libraries here. So so this code helps us to generate a bunch of random numbers. I've already written this. We'll add these libraries, and then I'm going to copy this code and write a function int generate random. Okay, max and min we are going to pass int max, int min, right? The range in which you have to generate the random number, and we return the num. Okay, so this random number we have generated. Now what we are going to do, we are going to say int l is equals to 0, r is equals to arr dot size minus 1. We are going to generate random number. Let's say pivot index is equals to generate random from r to l. Maximum value is going to be r, minimum value is going to be l. In this range always we are going to generate something. And then what we are going to do, we are going to call int x is equals to partition arr comma l comma r comma pivot index, right? Let's print x, and let's also print the vector. Let's also print the vector std cout arr at I. That's it. Okay, let's try to run this code. We'll say g++ partition minus minus std is equals to c++ 14 minus 4 run. Okay, dot slash run. Okay, so the pivot element is present at index 3. At index 3 you have 0, 1, 2, 3. So we have 4. Now you can see everything greater than 4 is to the right of 4, everything less than 4 is to the left of 4. And let's do one more thing. Let's print the pivot element also. Cout pivot is arr of pi. Okay, let's print the pivot also. Let's compile. Sorry, my bad. arr of pi. Let's compile again. Let's run. You can see this time pivot was 10. So everything greater than 10 is to the right of 10. Everything less than 10 is to the left of 10. Let's run again. This time the pivot was 3. So everything less than 3 is to the left of 3. Greater than 3 is to the right of 3. Let's run again. This time the pivot was 7. Less than 7 to the left of 7. Greater than equal to 7 to the right of 7. You can even have some equal elements. For example, let's say we have 2 7s only. Maybe we get 7 again as the pivot. See, every time the pivot is changing, right? See, now this time we had 7 as the pivot. Now if you see, oh sorry, my bad, I didn't compile. One second, I need to compile again and now run. Okay, let's see if we pick 7 as the pivot. See, now we have 7 as the pivot. So the pivot index is 4. So everything less than 7 is to the left of 7. Everything greater than or equal to 7 is to the right of 7. So our partition algorithm is working absolutely fine. And the time complexity of this algorithm is order of n. Time is order of n, space is order of 1. That's how you will implement the partition algorithm. And using this partition algorithm, we can implement quicksort. So the algorithm using which we have segregated all the lesser elements to the left side and all the greater elements to the right side is also called as the partition algorithm. Okay, cool. So we will write a function partition, right? We'll just get an array and we will get a pivot index. Okay, we'll get a pivot index. What is the pivot element? Pivot element will be the element at the pivot index. Right, okay. I'll start with a variable I that is going to be at -1 initially. Right. You can say that let L is equals to the start of the array and R is equals to the end of the array, arr dot length -1. Okay. So I'll initialize I with L -1. L -1. Right. Why I'm keeping L and R separately? Because it looks a bit better, like more readable. Also, and it is going to be used in other algorithms. This partition algorithm can be used in other algorithms. So there you will get the reference for L and R. Right. And then what I'm going to do, I'm going to write a function. Swap two element at index I comma j. Let temp is equals to arr at I. Arr at I is equals to arr at j. Arr at j is equals to temp. It's going to simple do the swapping. And now let's swap the pivot on the last index. So we'll say swap arr. Pivot index is what? This pivot index, right? And the last index is what? R. So I'll swap it at the last index, right? Okay. Now, what we will do is we'll say let j equals to, let's say j will start with L, and we say while j is less than or equal to R minus 1, right? We will compare. If arr at j is less than or equal to the pivot element, we will do I plus plus and we will swap the element at the ith index and the jth index. Otherwise, we are not going to do anything. At last, I will say swap the I plus 1th element with the rth element, that is the pivot element, and hence you will get the changes in the array. And that's it. So let's keep an array. Let's start with an array. So let's say 23, let's say something like this: 1 6 3 8 9 2 5. Okay. Pivot index I can keep as 2. I'll call partition algorithm. I'll pass my array and I'll pass the pivot index. And after this, if I will do console.log arr, let's see what happens. If I run it. Okay, so it's not ending because there is a very small mistake that I have done. I have used the variable j in the loop, but I have never incremented the variable. So I'll do j++ here. Okay, let's try again. Cool. So now technically everything lesser than 3 is to the left of 3, everything greater than 3 is to the right of 3. As simple as that, right? And let's see if we lost any element. 1 2 3 4 5 6 7. Okay, you have all of the elements also, so no problem at all, right? So this partition algorithm is working absolutely fine. And the overall complexity, if I talk about the time complexity of the solution is order of n, and the space complexity of the solution is order of 1. We are not wasting any extra space in order to complete the task.